First problem I have for you today is 29.A.3, which specifies this funny looking element A. A is namely the square root of 1 plus the cube root of 2. Notice the nested square roots. And the question says to give a basis for Q adjoin A. In other words, tell me what the numbers are that I need to make that I have to take all combinations of to produce the elements of Q adjoin A. Slightly odd statement for those unfamiliar with linear algebra, but if you're watching this video, it means you saw the previous videos, so you know what I'm talking about. In any case, this is really annoying, actually, to do without the machinery that we learned in this video. Or not in this video, in this chapter. So what I want to call your attention to is that I can start by figuring out what's going on with just the cube root of 2. And we've kind of seen that one before, right? The degree of this extension is 3, with a basis being given by 1 cube root of 2 squared, or cube root of 4. Right? This is a basis for this guy. And if I know this is degree 3, then I can think about Q adjoin A as an extension of Q adjoin cube root of 2. We can ask, what is that? And that simplifies the matter quite a bit, because setting x equals I have a equals the thingy. I don't need the letter x. A is the square root of 1 plus the cube root of 2. Then a squared is 1 plus the cube root of 2. And that actually lives in Q adjoin the cube root of 2, right? We did it. The polynomial is a squared minus this thing, or maybe I should say x squared minus this thing. A satisfies this. And so that means that this degree thing is 2, right? With its own basis being 1 over this thing and, well, x, right? Or this a, if you will. And so what this means is that in light of the proof of the theorem, and this is why I selected this problem, because oftentimes in this level of mathematics, it's not necessarily about the theorem itself, but about the proof. The proof of the field extension, the iterated field extension little theorem that we proved, or it's sometimes called the Tower theorem, is that a basis for the whole extension from top to bottom is given by multiplying the elements that appear in the individual components. So since this thing is generated by 1 and a over this guy, and this one is generated by these 3 things, then the overall basis must be given by all the possible products. So let's just write those down. First, we have the set 1 cube root of 2, cube root of 4. Then we also have the set 1a. And I have to look at all possible products of these. And so I have 1 cube root of 2, cube root of 4, right? Multiplying all the 1's in. And then all the a's, I have a times the cube root of 2, a times the cube root of 4. And if you look in Pinter, Pinter actually said this at the beginning, and I hid it from you guys because I'm just I don't know, I'm just dastardly like that, I guess. But he says to show that exactly this list is a basis for QA over Q, and to describe the elements. And that's what we've done here. We've applied this Tower theorem, and in particular, the proof of the Tower theorem, to concoct this specific basis directly. Very cool.